morning, it's Miss Manili, and this video is all about how to model nonlinear data. So far in Chapter 3, we have been looking at data sets that, for the most part, looked relatively linear in form, and we performed least squares regression to determine a linear equation to model the data. Well, in Chapter 12, we start looking at nonlinear data, and I actually think it's more appropriate to talk about nonlinear data now while we're on the topic of regression. I feel like it makes a little bit more sense. So basically what we're going to do in this section is we're going to look at data that is clearly not linear, and we're going to try to transform it using different operations to see if we can sort of reconfigure the graph to make it look linear. And if we can reconfigure the data using square roots or powers or logarithms or any operation really, if there's a way that we can transform our data to change the form to make it look more linear, then what we can do is perform least squares regression on the transformed data using the same methods that we just did in Chapter 3. So in Chapter 3, we learned how to analyze relationships between two quantitative variables that showed a linear pattern. When two variable data shows a curved relationship, we have to think about new techniques for finding an appropriate model. And it's nice when we have straight line data because there's really only one function to choose from. I mean, if it looks like a straight line, we use a linear equation. That's that. But when we have a curve in our data, there's a lot of different functions that come up. So for example, if we see a curve, it could be quadratic, it could be exponential, it could be a logarithm, it could be cubic or quartic. There's lots of different nonlinear functions from which to choose. So once we start looking at data that has a nonlinear form, we have to do a little bit of trial and error. And so it's not going to be as straightforward, I think, as when you have a linear pattern and you perform least squares regression on that. So in this section, we're going to talk about ways of transforming data so that we can straighten a nonlinear pattern, which seems kind of funny, but that's exactly what we're going to do. Once the data has been transformed to achieve linearity, then we can use least squares regression and all the processes that we just did in Chapter 3 to find a model to represent the transformed data and then make predictions from that. So throughout the unit, we've sought to model linear relationships using the process of least squares regression. Least squares regression can also be applied to nonlinear relationships through a process of linearization, and that's what we're going to do today. Linearization is simply the process of transforming your data. You can use any operation you want. For example, we're going to look at using logarithms, square roots, and powers. You can also take the reciprocal of your variables and explore the relationships that are produced from those transformations. And if you can somehow produce a linear pattern, then you can perform least squares regression on the transformed data. So let's take a look at an example. I believe we've looked at this data before, but this is data on stopping distance. Most drivers' manuals state that the number of feet required for a car to stop is a function of its speed. Makes sense, right? The faster you're going, it's going to take a little bit longer for you to stop, so your stopping distance will be a little bit larger. One driver's manual showed this relationship with the table below. So what I'm asking you to do, you might have to pause the video for a second, is to enter the data into list 1 and list 2 of your calculator. So we're letting speed represent our explanatory variable, so we'll call that x, and I'd like you to go ahead and put that in list 1. And then the stopping distance will be our response variable, y, so I'm going to go ahead and define them now, and I'd like you to go ahead and enter those values into list 2. And then what I would like you to do is sketch the graph. So produce a scatter plot, sketch the graph. Be sure to label and scale your axes appropriately. Describe the association between the variables, just like you did on the last test. And then in number 3, I want you to perform least squares regression. So go ahead and find a linear regression equation. And then report the values of r and r squared. Comment on their appropriateness. Does it seem to be a good fitting model based on those values? And then I also want you to produce a residual plot. And so please go ahead and press pause now and take a few minutes to complete page 1 of your notes. Feel free to work together if you need some help. You can also refer to the blue sheet with the calculator instructions if you need to. Okay. So if you've done this correctly, you should have a scatter plot that looks something like this, where we've got our x-axis represents speed and our y-axis represents the stopping distance. And if you're looking at that, I think you can see that there's a very strong association, that it's clearly positive, and it looks very, very linear. If you perform least squares regression, you should get these results, where you'll have a y hat is equal to 5.5x minus 75. And if you look at your r and your r squared values, they're very, very close to 1. So we can even conclude with our r squared value of 96.8 that 96.8% of the variation in the stopping distance can be explained by the linear regression equation on speed. And that's probably some of the highest values that we've seen in all of the regression models that we've calculated. So looking just at those numbers, I think we'd feel like we have a pretty good model. But once you look at the residual plot, I really hope that that stands out to you, because there is a very, very distinct pattern in that residual plot. That curve, this pattern right here, tells me that a nonlinear model is more appropriate. I should not be using a linear equation to make predictions about stopping distance based on the speed, because the data really isn't linear. And that's what the residual plot is telling me. So while we certainly can make predictions using the line, it's not terrible, but it's not as appropriate as a nonlinear model. So what we want to do is see if we can find a different function that might model this data a little bit better. And we're going to start by transforming the data. And I know it might seem a little strange at first, but what we're going to do is we are going to transform the data using the natural log. And natural logs are very common ways of transforming. It's a common transformation for data, and you'll see why in just a second. So what I'd like you to do at the top of list 3, we want to enter, so I'm going to do this on the bottom of the screen. So in list 3, we want to take the natural log of all of our x values. And since all of our x values are in list 1, I'm going to go to the tip top of list 3. The natural log button is underneath the regular or the common log button. So look for ln. So we're going to do the natural log, and I want to do it of my x values. And all my x values are in list 1. So I'm going to take the natural log of list 1. And it's going to seem really ridiculous because you're thinking, what does that mean? The natural log of my speed? None of those numbers make any sense anymore. And that's okay for now. And then what we're going to do is we're also going to take the natural log of the stopping distance, and we're going to put that in list 4. So in list 4, I'm going to take the natural log of my y values, or the natural log of list 2. So at the tip top of list 4, take the natural log of list 2. And again, you're going to see some numbers that really don't have a lot of meaning anymore in this context. Why would we take the natural log of the stopping distance? It seems quite silly. But the goal is to use these mathematical transformations on the data to see if there's a way that we can construct a new scatter plot using these transformations that might make the data look more linear. Because if I transform the data and then construct a scatter plot that looks linear, I can then do least squares regression on the transformed data. And I might get a better fit than I did when I did linear regression on the original data. So let's look for a model first, and then we'll talk about what to do with the model once we find it. So the first thing you're asked to do is to create a scatter plot. And so this is the first activity. We want to do speed versus the natural log of the stopping distance. And so that means my speed, the original speed values are in list 1, and the natural log of the stopping distance we placed in list 4. So what I'm going to do is I'm going to go back to my scatter plot. And again, it's just a regular scatter plot. I want my x's to come from list 1, and I want my y's to come from list 4. So I'm going to go into list 4. And then I'm going to hit zoom 9. And actually, let me make sure I don't have an equation in there. Okay, so when I hit zoom 9, this is what I see. Looks a little different than the original scatter plot. I don't know that it looks more linear because it just looks like there's a tiny little bit of a curve going the other way now. Then we're asked to construct a linear regression equation. So this time when I do my linear regression equation, I want to do it on the transformed data. So I'm going to go to my Stat menu. I'm going to choose Calc. I'm still going to choose linear regression, option 4, but I want to pull my x's from list 1, and I'm going to use the transformed values for the stopping distance. And so that is actually in list 4. So I'm going to do second list 4. And I am going to create a regression equation, and I'm going to store that in y1. Well, actually, because you guys already have an equation in y1, I'm going to store this in y2. So I'm going to go to vars, yvars, function, and this time I'm going to keep my original equation in y1, but I want to put my new least squares regression equation in y2. And so when I press enter, I get this equation, right? Now we got to be really careful when we're writing the equation, because the x variable in my equation still represents the speed, but the y variable in my equation is the natural log of the stopping distance. So when I write this on my paper, I want to write it as the natural log of y. Instead of y, I'm going to be writing it as the natural log of y, because that is the y variable I'm using. So the natural log of y is equal to, and I'm going to go ahead and enter my slope of 0.044. I am using the actual x's, my speed, and then I've got plus 2.745. And that would be the least squares regression equation based on the transformed data. The value of r is 0.702, or I'm sorry, 9702, which is good. And actually, that would round up to a 3, wouldn't it? And r squared is 0.9415. And the only reason I'm rounding to 4 decimal places is because you're going to, when we start comparing these models, you'll see that once we do these transformations, our values get closer and closer and closer. And so if you compare the r and the r squared values from this model to the one that we did with the original data, you'll see that these values aren't as close to 1 as our last model. So I wouldn't say, so if I were to actually hit graph here, I wouldn't say that that's any better, really, than the original model that I came up with. Those r and r squared values aren't any closer to 1 than what I started with. So I would rule this model out. So we want to try a different model then. This time I'm going to look at the transformation where I look at the log of my x values versus my actual y values. So in this next model, we're going to take the natural log of x and see how that looks with the actual y values. So this time I'm looking at the transformation using the data that now I have in list 3 versus list 2. And I understand if you are wondering why in the world I am doing this. Trust me, it'll make a little bit more sense in just a minute. So I'm going to go into my scatter plot or my stat plot setup. And so this time I'm going to change where my x's and y's are coming from. So this time, when I choose x's, I wanted to use the natural log of my speed, or the natural log of my x values, which are in list 3. So I'm going to change my x list to list 3. And I want to compare this to the actual y values, the actual stopping distance, which is in list 2. And I'm going to go ahead and zoom 9 it. And that definitely did not straighten the pattern at all, did it? So that curve looks even more curved than the last one. So if I do a linear regression equation, I would anticipate that the value of r and r squared would be closer to 0 than the last 2 models that I've looked at. But I still want to do it anyway because I want to show you how, even though this process is trial and error, and at this point I would probably realize that this combination of transformations isn't going to work for me, but I do want us to have like all 3 of them together so you can pick the one that's best. So I'm going to now do least squares regression, so I'm going to quit, and I'm going to do least squares regression, so stat, calc, and least squares regression again. It's just linear regression. but this time I'm doing it on the transformed data. But this time my transformations are going to be just on my x's, and so the natural log of my x's are now in list 3. So I'm going to choose list 3, and then I'm comparing them to my actual y values, which are in list 2. And for this regression equation, I'm going to store this in y3. Okay, and this is the information I get. So when I write my equation, I want to be mindful of the transformations that I did on x and y. So my equation that I'm given is y equals ax plus b, and the y is my actual y. So I'm going to go ahead and keep the y this time. The slope of my line is 174.281, but I'm not using my actual x's. I've now taken the natural log of x, so I'm going to say times the natural log of x, and then my y-intercept is a negative 459.819. So I don't have a ton of space here. And if I look at my r value, it dropped substantially, right? 0.8953. And the r squared now is only 0.8015. So that model is definitely one that I will rule out. It is not as good as the original linear equation that I came up with, or the equation that I came up with in the first exercise. So of all of them so far, this one's the worst. But I have one more transformation I want to look at, and this is when I compare the natural log of my x values to the natural log of my y values. And so my natural log of my x values are in list 3, so this time I'm looking at the natural log of x versus the natural log of y. And so I'm again going to go back up into my stat plot menu, and I'm going to create a new scatter plot, but this time I'm going to do list 3, because that's where the natural log of x is, versus list 4, and that's where the natural log of y is. I'm going to zoom 9 it again and watch what happens. Okay, so these lines that you're seeing, I'm going to go back and turn these off. So the equations that I have in y2 and y3 are the two linear regression equations I just did. If you go to your equal sign, if you highlight the equal sign and press enter, it'll turn it off. And that way it won't interfere with your graph and you don't have to delete it. So the equations are still stored in my calculator, but they've been turned off. Now look at that data. When you look at that scatter plot, I think you can see a very, very clear straight line relationship. So it would make sense, definitely, to do linear regression or least squares regression on this data. But remember, we transformed the data. It's not x versus y, it's the natural log of x versus the natural log of y. And so now I can perform least squares regression or linear regression if I go to my home screen. So I'm going to go to my calc menu. I'm going to still choose linear regression, but this time I'm going to do list 3 versus list 4. And I'm going to store this regression equation in y4. Oops, I did something wrong. Y vars, function, y4. There we go. And when I calculate, look what you see. I've got to be careful when I write my equation, because now x and y, I got to remember to write the natural log of x and the natural log of y. So I'm going to have the natural log of y is equal to, and the slope in this case is going to be 1.586, and that's going to be times the natural log of x minus 1.0195. That's actually just going to round up to negative 1.02. And if I look at my r value, notice that that actually rounds to 0.999. And my r squared is 0.9979. So about 99.8% of the variation. Now I want to be careful now, because it's not the variation in the stopping distance. It's the variation in the log of the stopping distance can be explained by this least squares regression equation on the natural log of my speed. So we've definitely kind of gone out there to kind of come back to have a model to make predictions. But I think it's pretty obvious now when I'm comparing my r and my r squared values that this model so far is the most appropriate. I think I have it all kind of, if you put them all together, this is what you see. So I think you can see very clearly that the transformations that we did where we took the natural log of x and the natural log of y linearized the data. And so then we could do least squares regression on that to get a much better fitting equation. And so where it kind of gets a little tricky now, if this is my equation, so if my equation now is the natural log of the stopping distance is equal to 1.586 times the natural log of my speed minus 1.01, I'm going to go ahead and keep the 9.5. So this is my equation, right? I have the natural log of the stopping distance is equal to 1.586 times the natural log of the speed minus 1.0195. If I wanted to make a prediction now, so like if I look at my original data, it looks like the speeds are all in multiples of 10. But if I wanted to predict the stopping distance for a speed, so let's say we let the speed, let's just do 55 miles per hour. And I wanted to predict the stopping distance, you're going to have to remember a little bit of your algebra here. But if I plug the 55 in, so I still have the natural log of the stopping distance is equal to 1.586. I'm going to need to take the natural log of 55 minus 1.0195. So I'm just going to go ahead and do this operation on my home screen. So 1.586 times the natural log of 55, make sure you close the parentheses, minus 1.0195, I get that the natural log of the stopping distance is equal to 5.336, which still doesn't really help me because I don't understand what that 5.336 means. I'm looking for the stopping distance in feet, and I'm not quite there yet because I have the natural log of the stopping distance. But if you remember, the base of your natural log is the number e. And if I wanted to solve this equation for the stopping distance, this goes back to Algebra 2, I would take my base e and raise it to that power, and that will give me the stopping distance. So if I take e to the 5.336, so I'm going to go, my e value is under the natural log in blue, and I'm going to go ahead and just highlight my previous answer, and I press enter, I get 207.707, so 207 feet approximately. And if we go back into our original data, doesn't that fit? The stopping distance for 50 miles per hour is 175. The stopping distance for 60 miles per hour is 240. 55 miles per hour, somewhere in between. And that's where the 207 fits. And I'd be able to say that this, I'm really, really confident in this prediction, mostly because I know I have a fantastic model and because my prediction is well within the domain of the values that I've collected. So we do kind of have to go off the beaten path by transforming the data and then kind of come back and untransform it to make predictions. But that's essentially what we're doing. We're still performing least squares regression, but we're doing it on data that we've transformed to make it look more linear. So how about if we make a connection between these transformations that we just did, and if you take a look in your calculator, so some of you might be wondering, like, when I go to that calc screen, the calculator has a ton of different regression options. There's quadratic regression, there's cubic regression, there's quartic regression. How does that connect? Why would I do linear regression instead of just doing the others? Well, they're connected. And so that's what this next little slide is about. And this, I'm only going to show you this once. It's not something that is going to appear very often, but just to kind of help you see the relationship between the linear or the least squares regression equation and the exponential, the power, and the logarithmic functions. We actually can linearize the equations. So if we think about the exponential function, I just used 3 as my base because I needed a base. So if we just look at the exponential equation, y equals 3 to the x, the two quantities that vary in this problem are x and y. And so if I use the natural log to transform the equation, and what I mean by that, if I take the natural log of both sides, so if I have the natural log of y is equal to the natural log of 3 to the x, if you remember back in algebra, if you take the natural log of a number that's being raised to a power, you actually have a property that tells you that you can bring that power and make it into a coefficient. So then this equation becomes the natural log of y is equal to x times the natural log of 3, or whatever the base was. And so if I think about the variable quantities now, the quantities that vary, taking the natural log of 3, I can do that on my calculator. That's just a number, some number. So the quantities that vary are x, and now I'm looking at the natural log of y. So my exponential equation, y equals 3 to the x power, is equivalent to this equation. The natural log of y is equal to x times the natural log of 3. So I can linearize, and if you think about it, because it's just my y variable, my output is equal to some number times my input. That's actually a linear relationship. But it's a linear relationship of x versus the natural log of y. So if you go back to the transformations that I did on the previous page, where I had x versus the natural log of y, so I linearized the data and did least squares regression on this relationship. This equation that I have here is going to correspond to an actual exponential regression equation. Let's take a look at the next one. If I have a power equation, y equals x to the second power, and again, it could be any power, it doesn't have to be 2. If I wanted to transform the equation using natural logs, if I took the natural log of both sides, so I have the natural log of y is equal to the natural log of x squared, I can take that power, again, just like we did before, and bring it out in front. And so then I'm left with the natural log of y is equal to 2 times the natural log of x. And again, I've got an output is equal to some number times an input. That is a linear relationship. It's y equals mx plus b, if you think about it, right? We have our output is equal to some coefficient times another variable. But the variable quantities in this linear relationship now are the natural log of x versus the natural log of y. And so when I take the log of x and the log of y, that's the same as if I were to do power regression on the original data. And finally, if I take a look at a logarithmic equation, right, we look at this equation y equals 3, and I just used 3 to have a number there, to have a coefficient. If I look at this logarithmic equation as y equals 3 times the natural log of x, well, I can also look at this as a linear relationship because it's just my output is equal to some number times my input, except I'm looking at that variable quantity as the natural log of x. That whole quantity is going to vary every time I plug in a new number for x. So it turns out that if the natural log of x versus y produces a straight line pattern, that's going to correspond to logarithmic regression. So I know it's a little weird, right? So if I am looking at data on x and y, and I transform it, and the relationship between x and the natural log of y is linear, that's the same thing as if I were to perform exponential regression. I'm going to get the same model. It's just going to be transformed. That's going to correspond to exponential regression. If the transformation of the natural log of x versus the natural log of y looks linear, then I would actually just go ahead and do power regression using these original, if I look at my calculator, I would just go ahead and use those original commands. And if the natural log of x versus y is linear, then that would correspond to logarithmic regression on the original data. So let me show you what I mean. Okay, and so in number 5, it says, consider the relationships of the transformed variables you explored in number 4. Which relationship linearized the data? It was the natural log of the speed versus the natural log of the stopping distance. And then it says, what algebraic function corresponds to this relationship? This would be our power function. So it says to perform regression analysis on the original data. So we're looking at speed versus stopping distance. That's my original x versus y using this function. So what I'm asking you to do is to find your power regression command. So scroll down. I think it ends up being letter A. So we are going to do power regression on the original data. The original data was in list 1 and list 2. And I'm going to put my regression equation, whoops, in y1. Oops. And I'm going to go ahead and calculate. And so I'm going to be careful because I'm still given an a and a b, but the a and the b here are not my slope and y-intercept. If you look at the top of your screen, you'll see that the power regression equation is of the form y equals a, which in this case is 0.361, times x raised to the power of b, and in this case b is 1.586. Now take a look at your r squared and your r values. These are the same r and r squared values for the relationship between the natural log of x and the natural log of y. So we can transform the equation or we can transform the data. But when we're looking at the relationship between the log of x and the log of y, that's going to correspond to a power model. So let's just rehash this a little bit before we jump into any other types of transformations. Not all of the transformations we do are going to correspond nicely to another model, but if x versus y, whoops, and this, I know there's not a space on your paper for this, but you might want to write this down. If x versus y is linear, whoops, then you're going to perform linear regression, right? If, let's take the natural log of x versus y is linear, then you're going to perform logarithmic regression. If x versus the natural log of y, and it doesn't have to be the natural log, it could be the common log, it could be the log base 3. It actually doesn't matter what base you have. So if I'm looking at the relationship between x and the natural log or the log of y, if that relationship is linear, that's going to correspond to exponential regression. I could do exponential regression on the original data. And finally, if the natural log of x versus the natural log of y is linear, then that would correspond to power regression. And you may be wondering, since this is so out there, how will you ever remember this? Well, I'll tell you how I remember it. If it's just flat out x and y and that's linear, that's easy. That's what we've been doing. But for the transformation where I've got the log of x versus y, since the log of x is the only transformation and that comes first, that's going to correspond to log regression. In the next one, I've got x versus the log of y, so it's a transformation, but I'm starting with my x. It's going to correspond to the exponential regression. And this is where you're going to laugh at me. But if I'm looking at the log of x versus the log of y, log versus log, and I'm sorry that you can't see me do this because most people just laugh at me, but I think log, log, and then I think pow, pow. And that's how I remember power regression. So if it starts with the log of x, I know it's logarithmic regression. If it starts with x, it's going to be exponential regression. And if it's log, log, it's going to be pow, pow, power regression. And so basically what that means is I can perform linear regression on the transformed data, or power regression or exponential or log regression on the original data. I know that's a little confusing. I just need you to sort of bear with me for a little bit. But the logs, those aren't the only kinds of transformations that we can do. If you take a look at the next set of exercises, we can also use square roots. I could also square my data. So I could take x squared versus y. I could take the reciprocal of x and the reciprocal of y and compare those relationships. It's really infinite, the number of transformations that you can perform to achieve linearity. So there's not only one possible model. You may do 10 different transformations and come up with an equation that you think is best, and someone else could outdo it with a different type of transformation. And the goal isn't to try to make this too complicated. We just want something that's going to be a reasonable fit that we can use to make predictions. We model all the time. If you go to the Weather Channel, there's probably 6 different places you can go to get the weather. They probably all use different systems to model the weather to make predictions on what it's going to be like. So it's not like there's only one model and it's the only model that can be used. Lots of different models can be used for data. Obviously, if it's worth anything, you want to make sure you have a good model. In number 6, we're going to take a look at transformations using the square root. And this is something I'm actually going to have you guys do together. I'm not going to have you sit and listen to me for another half an hour. I'm going to actually ask you guys to do this as a class or together using small groups. And so in number 6, it says the natural log is one of many transformations, like I said. And this time we're going to look at another transformations using the square root. So what I'd like you to do in list 5, we're not going to delete anything that we've already done, but we're going to now work with lists 5 and 6. And we're essentially going to do exactly what we did before, but we're going to be using the square root. So in list 5, so I want you to go back to your lists. And what I want you to do in list 5, if there's anything in there, just clear it out. This time the transformations that we're going to be comparing is going to be the square root. So I'm going to take the square root of my x's, which are still in list 1. I haven't moved them. So I'm going to take the square root of list 1, and that's going to go in list 5. And in list 6, I'm going to take the square root of all my y values, or my stopping distances. So the second square root, and I'm going to do that from list 2. So take the square root of all my y values, and I'm going to press enter. Okay, and so now what I want you to do is you're going to do it 3 different ways. So we're going to look at speed versus the square root of the stopping distance. We're going to look at the square root of the speed versus the stopping distance. And then we're going to look at the square root of the speed versus the square root of the stopping distance. So when you're constructing your scatter plots and doing your regression, in the first example, you're going to be doing list 1 versus list 6. And then in the second example, you're going to be looking at list 5 versus list 2. And then in the third one, you're going to be looking at list 5 versus list 6. We could seriously go out there and also look at combinations of square roots and logarithms if we wanted, but I don't want to go there. Now we're going to look at the transformations using square root only. So what I'd like you to do is stop the video, or pause the video, sorry, and I'd like you to go ahead and work with the people around you to construct scatter plots. And again, we're just doing least squares regression, so we're going back to doing linear regression, but make sure you're performing it on the lists that are indicated in each of the columns. And then report the r and the r squared value. And let's see if we can come up with a model that's even better than the one that we came up with in the last example. So again, please pause the video and come back on in maybe 10, 15 minutes when you're done. Okay. So now if you look at the data, this is now using the square root transformations. And we've done least squares regression on each of these. If you look at that very first relationship, this is the speed versus the square root of the stopping distance. You can see an almost perfect linear relationship. And if you look at your r and your r squared, you'll see that this transformation results in a linear relationship that is even more perfect than the last one we came up with. So it says, which regression equation is the best model for the data, and justify your response. So when I write this equation, So I'm going to go ahead and write the equation for this relationship. I'm going to make sure that when I write my x and my y, that I'm using the transformations from that experiment or that relationship, right? So my y, so this is x, and then this is the square root of y. So we're saying basically the square root of the stopping distance is equal to 0.229 times x, which in this case is the speed. I'm going to actually just put my variable names in here because I think it helps a little bit. And then the y-intercept in this case is 1.708. And I'm going to say that this is the best model for the data because not only is my correlation coefficient almost 1, my r-squared value is almost 100%. So almost 100% of the variation in the square root of the stopping distance can be explained by this linear model that's based on the actual speed of the car. And it says, is this model better than the one we chose in number 4? Yes. Not by much, but yes, it's better. And then it says again, use the best model to predict the stopping distance for a car traveling 55 miles per hour. So we did that with the power regression, or the relationship we saw in the other example. But let's go ahead and do it here. I've got my stopping distance is going to be equal to 0.229 times the speed, which we're going to go ahead and use 55, plus 1.708. And on my calculator, I'm going to do let's go into my, there we go, 0.229 times 55 plus 1.708. And when I press enter, I get 14.303. Well, remember, that's the square root of the stopping distance. So if I want to find the stopping distance, I need to square both sides. So the stopping distance would be predicted to be 204.576, and that would be in feet. And so that would actually be a more accurate prediction based on this model, because this is actually a better model than the one we had before. Okay. If we take a look at the last page, whoops. If we take a look, that's not what I wanted to do. Sorry. Okay. If we take a look at the last page, and this is how I would expect it to be presented to you on the AP exam. So the nonlinear regression, it's not something you're going to be assessed on in this course, like in AP Statistics in Anne Arundel County. As a county, I'm going to give you a little assessment on this next week, but I'll talk about that in just a second. On the AP exam, what I would anticipate, and this is what I have seen on several exams, is you're given the output and then you just have to interpret it. So if we take a look at problem number 7, it says this is the data on distance from the sun and the period of revolution of those planets. So like how long it takes for those planets to revolve around the sun. It says that the distance is measured in astronomical units and the number of Earth distances the object is from the sun. So it's not in miles, but it's in Earth years. And I guess it's not distance, it's the time it takes to revolve around the sun. So if you take a look at the data for the different planets and you take a look at the scatter plot, I see a definite positive association. It seems to be very strong. And if I'm glancing at it, it looks fairly linear. So if you take a look at letter A, it shows you the graphs below show the results of 2 different transformations. So I have to look at my axes to see what transformations were done. So if I take a look at the first one, I didn't do any transformations on x. Notice that it's the straight up distance. So in this graph, it's just going to be distance versus, but if I take a look at my y values, I'm looking at the natural log of the period. So in this relationship, I'm looking at x versus the natural log of y. And then in part B, this is a different transformation where I'm looking at the natural log of the distance versus the natural log of the period. So we actually are looking at the natural log of x versus the natural log of y. And so what I would do in letter A is explain why a power model would be a more appropriate description of the relationship between the period and the revolution than an exponential. So if I take a look at the first graph, remember, if x versus the natural log of y is linear, that's going to correspond to an exponential model. And if the natural log versus the natural log, that's going to correspond to power. Remember, log is pow pow. So that would be a power regression. And so in this case, because the natural log of x versus the natural log of y produces the most linear relationship, or I could say since the natural log of x, well actually let's use the actual variables. Since the natural log of the distance versus the natural log of the period linearizes the data, a power model, and I should say linearizes the data more so than the other transformation, a power model, and this would be on xy, would be more appropriate than an exponential one. Okay? And so then in letter B, you are given the output. So notice that you're not really having to do any calculations. You are given the output in letter B. Minitab output from the linear regression analysis on the transformed data is given below. Give the equation of the least squares regression line and be sure to define any variables you use. So this is least squares regression on the natural log of x versus the natural log of y. So when I write my equation, and remember these are the numbers I use, when I write my equation, I have to make sure that with my variables, I'm writing them as the natural log of x and the natural log of y. So I'm actually going to use my actual variable names to help hopefully reduce the confusion. So y in this case was the period. So I'm taking the natural log of the period is equal to, and so my slope is going to be 1.4, I'm going to just go ahead and write all the numbers here, 0.9986. The x variable in this case is the natural log of the distance, and that's going to be plus 0.000254. So that is the least squares regression equation. So Minitab has performed linear regression on the transformed data. The alternative would be to perform power regression on the original x and y. And while your equations are going to look different, your prediction should be the same. So in letter C, it says to use your model from part B to predict the period of revolution for Eris, which is, I'm not even going to say that word, 102.15 aeronautical units from the sun. And so this is my x value, right? So when I plug that in, I'm going to have, again, the natural log of the period is equal to 1.49986 times the natural log of 102.15 plus 0.000254. I'm going to go ahead and simplify the right-hand side of my equation. And 0.0002544. And I get this. So I have the natural log of the period is equal to 939. And again, if I want to solve for the period, I'm going to remember that when I'm dealing with natural log, my base is e. So essentially, I'm going to take e to the 6.939 power, and that's going to equal the period. And so on my calculator, I'll just do e, and then if I just highlight the previous answer, I can type that in. And so we get 1032.017. And that would be in Earth years. And if I take a look at my original data, because 102.15 is so far beyond my data, Would I be confident in that answer? So if I think about it, the highest value from the distance of the sun is only 39. And in this case, we're looking at 102. So right now, I know that this is an extrapolation. And so because it's an extrapolation, I'm probably not going to be very confident in it. But if we look at letter D, we can also see this is the residual plot for the linear regression from part B, shown below. And so if you think about it, it's kind of hard to estimate this, but if you see that residual plot, I can actually see that the regression equation that I came up with, even though the value of r squared was 100%, because I see the curve in this pattern, I probably wouldn't be very confident in it. But in any case, when I'm looking at the natural log of 102, I think the natural log of 102.15 is about 4.6. So on my residual plot, that's going to be somewhere over here. And so I would expect my value to be above the line. So if this is where my prediction is, I would expect my prediction to underestimate. But again, it is an example of extrapolation, so for that reason, and the fact that there's a pattern in my residual plot, I wouldn't be very confident in that prediction either way. So I know I've thrown a lot of information to you at once, and I'm not present to answer any questions. So I'm not going to give you any homework right now. Just focus on reviewing for your quarterly assessment. Nothing from this video is on the quarterly assessment, but we will revisit it next week when I'm back, and I'll answer any questions you might have at that point. So have a great weekend, and I will see you guys next week.